Okay, so last time we looked at numerical simulation of granular flows in which the motion of each particle is considered. And here we are considering n particles of mass mi, and they have a position at any time of xi and a velocity vi, but also an angular velocity omega I. And there will be body force, gravity, interparticle forces, and torques. And these are the governing equations, but we'll look initially at least for just as an illustration purpose, we'll look at frictionless particles. In that, there is no tangential force, hence there is no torque and no moment of inertia or angular velocity required. And in this case, we saw that the governing equations are mass into acceleration is the sum of the interparticle forces plus the body force. And then the rate of position, change of position is just the velocity. And in this equation, Fij is the force exerted by particle j on particle I. G is the acceleration due to gravity. And of course, we saw that since there are so many particles and they're all interacting with each other, you have to have a numerical solution. And there are two methods that we can use for this solving this problem. One is the hard particle or event-driven method, in which we assume that the collisions are instantaneous or the time for collision is 0. And in this method, as we saw, we integrate from collision to collision. And this type of, though I didn't mention it, but this is best suited for rapid flows and low volume fractions since the time between collisions is sufficiently large. And then the other method is the soft particle method, which takes into account deformation of particles during a collision. And so you need a time step that is 50 times smaller than the collision time. So this is best suited for slower flows with high volume fraction. And of course, you can easily simulate static systems also, and we'll do that. Excuse me. So then let's look at what are the steps for the hard particle method or assumptions. So at any given time, only one collision can occur. And between any two collisions, your force, interparticle force is 0. So there's no, in this equation that Fij just goes away. And particles, hence, at any given time, they move independent of all other particles. So now you just have these equations. And so since there's everything depends only on I in all these equations. So for each particle, we can integrate these equations independently of the other particles. So particles move independent of all other particles between collisions. And so then the procedure is calculate the collision time at which the next collision occurs, move particles until this time, and then update velocities of the colliding particles. I'll also show you this that, if the density becomes too high, then you can go into this inelastic collapse where, the time between collisions becomes smaller and smaller. And so in a sense, you will get infinite number of collisions in a finite time, like we saw in the example of inelastic collapse. So this is how we had done it. Let's say xi prime is the position after time delta t. If the initial position and velocity are xi and vi. At the time of collision, that is when the two particles are just touching, this minus this is equal to 1. This is the absolute value or a magnitude, you can say. And when you simplify this, you substitute for this equation and then simplify, we get this, which is a quadratic equation. And then you can calculate delta t, and a collision will occur only if b is less than 0 and if B squared is greater than 4AC. Now, one of the things that I didn't mention in the previous class, but it is important, that we always have to take the minus sign over here. So you will have actually over here, it is actually plus or minus. Since B is negative, that means the first term over here is positive. And so you'll get two terms. The term in the brackets is always going to be less than B, since both A and C are positive. So B squared minus 4AC is always going to be, square root of that is always going to be less than B. So you'll get two positive roots if these conditions are satisfied. So you should always take the smaller root, because, you know, when they just touch is one solution to the equation. But what happens is that, you know, since the particles are all moving independent of each other, they are free to go through each other. So what happens is that this particle, let's say, is moving, if we are looking, keeping xj fixed and moving xi, then this particle, let's say, if it's moving in this direction, then, you know, after some time, that particle will be here. So you actually have two roots where it touches, and so this is the first collision, and then the particle passes through the whole second particle, and then it again satisfies this condition, and that is the second root. So you have to take always the smaller root. And so this is what it is, that you move all, after you calculated the collision time for every pair of particles, then you move them by the minimum value of delta t, and this is the equation that you use to move them. And then for the particle I and j which are colliding, then you update the velocities and so forth. And you can do the same thing for wall collisions and all this also. So this is the basic algorithm, and I gave you a small demo. Those programs I'm going to put on Moodle, where the initial positions and velocities are shown in this orange and gray. Then when you go through the whole thing, it turns out that these two particles are the ones that will collide. You can see this is the velocity over here, this is the velocity here. So the particles move along in that, and they are the first to collide. And you know, after collision, the velocities are shown by the black arrows. So this is the calculation. So once we have known this, then we move all the particles by that time delta t, and so you can see every particle has moved. And of course, they will move all different amounts because the velocities are different. This one has hardly moved, and this one has moved a lot. And these two which are colliding, they have collided, but now their velocities are updated, so they are moving apart. All the others, the velocity remains the same. The velocity is, even after moving, is exactly the same. Okay, so this is what we had done in the previous class. Now, what I'd like to do is, of course, I want to show you some demos of this again. So let me share my whole screen. Can you see this? Can you see this terminal?
Yes, sir.
Okay, good. Now, this I showed you last time. So, you know, in a sense, I don't know if how many of you are familiar with all this, but the program is written in C, and it's called box 1. So this is the program which I showed you. Okay. And as I explained to you that it's essentially follows the same algorithm that I mentioned. This is reading in the positions and velocities of the particles. Then it checks for collisions and calculates the minimum collision time. And then it prints out what is this pair that is colliding and time. And then it moves all the particles by that amount of time. And then it updates the velocity of the particles I min and j min which have collided. Then of course prints out their values and writes down the positions again. So, I have just since this is like in Unix. So in this you can actually write down these kind of scripts in which a series of commands are executed. So here it says remove star.dat, that means remove all files which have .dat as the extension, then compile the initialization program, run it, compile the program box, run it. And then there is a graphics program called GNU plot which I use to plot the positions. So this is what it is, and I ran this last time also. So it's actually doing the calculations in front of you. And here, as I told you last time, the particle number 18 and 19, this is I and J. They collide after time 0.86 seconds. But particle 2, which is this one, will collide with the wall, with this wall. So that I haven't really gone into, but just as you get collision time with each particle, you can also get collision time with the walls. So particle 2 collides with this wall after 1 second. So it's obviously this collision takes place first. And so we saw this, we've seen it many times, and that's it. You can go to slightly more complex thing. And here, we want to run it for longer period of time. So when I say run, what it does is it will run the same program, but now it's not the box 1, it ran it only up to the first collision and stopped. In this program, it keeps on running it for a long time, for many collisions. So you can see here that after several collisions have taken place, and it says that the average time between collisions is 0.002 because I have taken a lot of particles. And this is the plot of the kinetic energy versus time. So you can see because the collisions are inelastic, the kinetic energy is reducing with time. And if you plot 1 by square root of the kinetic energy, you see it linearly increases by time. And we'll see why when we do the theory for this granular. Somebody's this thing is not muted. Can you mute it? Thank you. So this is what. So this is actually the initial condition. This is the initial positions of the particles. And this is the initial position, and each of the particles has some velocity. So I didn't show you that first. And then when I run it, this is the new positions of the particles after a certain amount of time. I think number of collisions is fixed. And then you can see this is how the kinetic energy changes, and this is how the one of the things that we can do is we can change the this third one here is actually the coefficient of restitution. We have put it as 0.9 in our case. If we keep it at 1, so this is now coefficient of restitution as 1. And now if I run it, what you will see is here is the position of the particles. And you see, can you see the orange lines? Huh? Is it visible to you?
Yes, sir.
So you can see that if coefficient of restitution is 1, there is no loss of energy, and as required, the kinetic energy is constant. Okay. And of course, the square root of this is also a constant. Now I'll go to the same thing. These in the third example, I'm going to run a program called box 1G. This is the same as box 1, but this time there is also gravity acting. In the previous problem, there was no gravity acting. So if I do run 1, you see that these particles have actually different set of particles. Actually, it starts with the same way. Okay, I think I'll just do it again. So first I'll. Oh. Okay. I'll initialize it first. And then I'll show you the initial positions, which are exactly the same as what were there before. So this is the initial positions of the particles, and these are the initial velocities. So this is exactly the same as the box 1G. And then now if I run it, run 1, so it will run till the next collision. And you can see now it is not 18 and 19 which are colliding, but because of gravity, it's actually number 2 which is colliding. And this is what it says now. 18 and 19 collide after 0.86 as before, but particle 2 collides with the wall at a shorter time, 0.84. That is the first collision. So that's what happens. And so now we have moved all the particles forward. And now if I run it again, starting from where I did, now you'll see that 18 and 19 will collide. So now this is 18 and 19 have collided with each other. And now the new velocities are like this. But now you see all the particles are all trying to fall down because there is gravity. And the collision time for this was 0.016. And that's it. And then I finally want to show you example number 3. I mean example number 4. Now this is the same program as box, but it's called box G. And this one I'll initialize it. Then I'll show you the initial position, GNU plot, and plot the initial configuration. So this is what the positions are, and these are the velocities. So this is exactly what we had for the program box, but only thing now here there is gravity. So what actually happens here is, if I run it, you see this is the initial, it's plotting still. So it ran it, and look what happened. All the particles have just settled down, and look at the time, average collision time, 0.0009. Because now the particles are so close, you can see their velocities, they're all going down, but the particles down here, their velocities are almost zero. And if I do a magnified view of the particles, you can see that they're actually not touching. If you blow it up more and more, you'll see that there's a small gap between them, really tiny gap. And the particles are simply bouncing against each other. That's why the collision time is so short. And then if you look at the kinetic energy, because of gravity, the potential energy gets converted to kinetic energy. So first the kinetic energy rises, and then because of inelastic collisions, the kinetic energy falls. So here I've run it again, and you can see that the particles have even come closer, and the average collision time has reduced even more, 0.0004 from 0.0009. And here are the velocities. You can see now they are even smaller. And here you can see all the particles just touching. And the kinetic energy has come to a smaller value. Okay. So these are all available to you. You can play around with these and see, how uh, how things will change as you change the parameters and so forth. But what I wanted to show in the last example was that as you go towards more and more dense systems, this hard particle method becomes less and less efficient as the time step becomes smaller and smaller. So the rate at which the simulation is going forward reduces to a great extent. Okay. So any questions? Okay, if not, then let's go back to looking at the next thing.
Sir?
Yeah, go ahead.
Sir, when you share the files on Moodle, could you also provide a tutorial on how we can run these files?
Okay.
Like the
So
commands you just gave.
yeah. Okay. So one of the things that I'd like all of you to try out is uh, on your laptops, if you're using Windows, can you all load Windows subsystem for Linux? Are you aware of this?
No,
Has
sir.
anyone heard of this WSL?
Yes, sir.
So please load it and see. Then if you open a terminal in that, it will look like what I was doing. And there I can tell you some of the commands and so forth. Yeah, I'll be happy to do a tutorial. But just get yourselves ready because you'll need it even for running the LAMPS programs, which is what is the main thing that we'll use for doing the simulations. So now I'd like to move on to the next uh, topic, which is soft particle simulations. Okay. So here, the deformation of particles is taken into account. So, you need to resolve the deformation in each collision. So to do that, typically your time step with which you advance is about the collision time divided by 50. So you have 50 time steps. You remember we had done that example where the two particles come together, then they overlap, and then they go out. So that whole process has to be numerically simulated. And so you have to go to a very fine time step, which is, let's say, around 50 times smaller than the collision time. And we saw that the collision time for, many of the materials is about 10 raised power minus 6. So you'll have to go to sufficiently small time steps. Okay, so this is one factor. And what you really need to solve these is a force law. We've seen one, which is the Hertz law, but we'll consider linear viscoelastic one also. And in this example that I'm going to do, linear viscoelastic force law, just as a simple simplification, in which the force Fij is just equal to minus kx times alpha minus kv times Vn. And of course, force is generally a vector, but here I'm showing the magnitude only. And what we say is that Fij acts along the line joining the centers of the colliding particles. So basically, if you have these two particles which are colliding, Fij is going to act in this direction along the line joining them. And then of course alpha we have seen before is just 1 minus the absolute value of xi minus xj, and alpha has to be greater than 0. Otherwise, this is true only for alpha greater than 0. Otherwise, Fij is equal to 0. So that means the force is only when the particles are touching. Beyond, otherwise it doesn't. It isn't. And the other parameter there is the normal velocity. So this is Vi minus Vj dotted with xi minus xj divided by the magnitude of the distance. So this is the normal velocity, or I should say relative normal velocity. So we are really looking at a simplification where there are no frictional forces and so forth. And so there's only the velocity to be taken into account. And when two particles interact, the force only acts normal to the surface of the particles. So here, if we look at this, the first term, this is the elastic contribution. It's like a Hooke's law or a linear spring. And if you look at the second term, this is the term related to viscosity or viscous contribution. So you can say this is nothing but viscous damping. So there's a linear so this term is purely elastic, and this term, the second term, gives you the, so this term is purely elastic, and then this one gives you the energy loss due to viscous dissipation. For this model, we can easily calculate, as we had done for the Hertz model, so time for a collision. So the time, we can calculate the duration of a collision. That is, in this case, just given by pi by b. I'll define what is b. And the coefficient of restitution, in this model, you can calculate that also. Call it as epsilon. And that is nothing but exponential of minus pi into a by b. So these are two important parameters, and this a is just equal to kV by 2 and b is equal to kx minus kV squared by 4 raised to the power of half. So these two are, so once you know kV and kx, so for purely
So you're muted.
now,
Yes, sir.
I wonder how it happened anyway. So for purely elastic particles, kV is equal to 0. So in this equation, if you see, if it's purely elastic, then this term will be 0. And then if you look at that, you see that if kV is 0, that means A is equal to 0. That means your coefficient of restitution is equal to 1. So this is as expected. So this is the sort of broad definition. So we are looking at a simpler problem. We are looking at particles in which interact with this force law. And how do we then solve this? So the algorithm is, the computational algorithm is just like this. So the first step is compute list of neighbors for every particle. Because you have to calculate Fij at every time interval. So you don't want to keep searching and finding out which are the neighbors. So find out who are the neighbors, and how do you find out the neighbors? Well, let's look at all particles whose distance xi minus xj is less than some range. This is some number, let's say 1.2 or something like that. So you're looking at all particles which are, of course, this number is always going to be greater than 1 or equal to 1. So you want to look at particles which are close enough so that, let's say, over the next time step or so, they may actually start touching. So you don't want to miss out any of those. So you keep this large enough so that no particle from outside this range can collide with the other particles. So this is the list of neighbors, and this you need to calculate. And the same list maybe you can use for more than one time step. Then next is to calculate Fij, that is the force acting on I due to all particles j for every I particle. So using the neighbor list. And then the third step is update the positions and velocity of the particles using this equation. Like the new position xi prime is just going to be xi, and then vi prime is equal to bi. So j going from 1 to n of Fij times n, which is a line, Nij is the vector along the line joining the centers. So this has to be a vector equation, plus g hat, this whole thing multiplied by dt. So this is a simple Euler step. It's called the most inaccurate, but okay, the simplest. And let's say if the range is equal to 1.2 and if Vmax is equal to 2, so then the minimum time for two particles to collide who are not already neighbors so if they're not in the neighbor list. That is, let's say, supposing you have a particle that is just at or little greater than a distance of 1.2. So that means it's not in the neighbor list. And then suppose we don't update the neighbor list and then we keep on integrating. So that particle will keep on moving. So the worst case scenario is that it will move through the distance 0.2 in a certain amount of time. So if Vmax is 2, then the relative, and let's say both the particles are moving with a velocity 2 in opposite directions, then the total velocity is 4. So then the time for the particles to move through a distance 0.2 is just equal to 0.2 divided by 2 times. I'll write it as a formula first. So let's say it's range minus 1, because 1 is when they collide, divided by 2 times Vmax. So if we substitute the numbers, then it's 0.2 by 4, which is 0.05. So now if we take, let's say, dt to be equal to 10 raised to the power minus 3, then this implies that we can actually go for a time delta Tc before we update the neighbor list. So the number of steps before we update the neighbor list is going to be just delta Tc divided by dt, which is equal to, well, this turns out to be 50. So we can go 50 steps, because this is a very, very expensive process of calculating the neighbors. So it basically goes as, if there are n particles, then you have to go roughly, you have to make n squared calculations, roughly n squared calculations to get the full neighbor list. And that is the most expensive part of the calculation. So you'd like to reduce that to the extent possible. So if you have this range as 0.2, then after every 50 steps, you can calculate the thing. There's some balancing, because if you make the range too big, let's say you make it 1.5, then you need to calculate the neighbor list after a longer time. But then the problem is that you'll have number n over here, in this thing, n is the number of neighbors for a given particle, then that number becomes very large. So then this calculation becomes very expensive, because you're summing over each neighbor of I. So if your range is too large, then n becomes large. If your range is too small, then ns becomes too small. So there's some optimal that you can achieve. Okay. So this is a very, very straightforward sort of method, and it's just straight numerical integration of the original governing equations. Unlike in hard particle, where you could get some part analytically done, here not possible. So we can, again, I have got some programs which are exactly like what we did for the hard particle simulation, just for comparison. So let me then just give you a brief demo of that. So I'll just share the screen first and then show you these. Okay. I hope you can see this. So here we looked at hard particle, now we'll go at soft particle simulation. So exactly the same things. I showed you EX1, EX2, EX3, EX4. Same thing, but now for hard particles. CD means change directory. So change directory to EX1. LS means list. So again, I have this same sort of thing. You'll see there's box 1, which is the C program. There's ini, which actually creates the initial sort of initial configuration and velocities of the particles and so forth. So let's see if I run, I can show you this. So you see this, it starts with the same thing. So I want to just show you that it's exactly the same. These are the velocities, positions, velocities. Notice 18, 19.
Hello, sir.
Yeah.
So the screen is not visible.
Okay. Now?
Now, sir. Okay,
Yes, sir. Now we can see.
Okay. So let me start again. So if we if we run this, if we just execute this script called run, run is just a series of commands. So it says remove all the data files, compile the program ini.c, then run it, then plot the initial positions, compile the program box1, run box1, and then plot the positions of the particles after running, and then plot, as a check, how does this result compare with the hard particle case? Okay. So that's what it is. So let's run this. So this is the initial position, initial velocities. Again, what I wanted to say is that 18 and 19, you remember, they are moving towards each other. They are the ones that will collide. That's what happened in the hard particle case. And here 2 is also one which collides, but with the wall at a slightly later time. So if we then let the program run, you see this is the position of the particles after colliding. And the time for collision is slightly different, about 0.88. Okay, and the time duration for the collision is 0.03. So we have taken kx to be 10,000, kv to be 4.74, and the coefficient of restitution is 0.9. So this is the positions of the particle after the collision has taken place, position of all the particles. So this is just to compare to what we saw for so 18 and 19 have collided, and then this 2 is pretty close to colliding with the wall. But the time for collision, you notice it's slightly different. And the reason is now the collision time itself is finite, and that is given by 0.03. And so now here it's the initial positions and then the position after collision. And the green arrow shows what it is with the hard particle, and the black arrow shows with the soft particle. So you can see that there are slight differences, and that is to be expected since the there's a physical difference between these two situations. In one, the value of kx for the hard particles is basically infinite, and the time of collision is 0. So this number is infinity and this is 0. Whereas here the number is 10,000, and so that's why time of collision is so much. Now this kx is actually very it's small. It should be maybe 100 times larger, in which case the time step will also be 100 times smaller, and then then the class will go on for longer than what you will be willing to listen to. That's why I'm doing it for a soft particle, really soft particle system. We can go to the next example, just like the case for soft particle, for the hard particles. And here we have for many of the particles. So again, this is the program run. So if I just do this, this is just remember exactly like what we did for example 2. This is the velocities. This is after certain collision time. And this is how the kinetic energy changes. Of course, this time is much, much more than what we had for the hard particle case. So we have run it for much longer, much larger number of collisions. And this is what the collisions look like. Oh, this is for the case of, this is for the elastic case. So okay. Okay, so here I'm going to stop over here because there's the main problem in these soft particle collisions. And if I just run this again, so I should sort of tell you this. The main problem in the soft particle collisions is that, in soft particle method, is that the system can be unstable. So this is the example where the time step is too large, and as a result, the system is just blowing up. Now in this is an example where kx is 1000, it's very soft, but kV is 0. kV is 0, that means it's an elastic system. And in this case, we saw that for the case of hard particles, a kinetic energy rest remained constant. But in here, you see the kinetic energy is just increasing and increasing by a lot. So this means that the system is unstable. And you can see that, look, all the particle velocities have just become so huge. And in fact, as you go on, the kinetic energy keeps on shooting up. And look at the velocity. They've just become very large. And look at the overlaps between the particles. So, the velocity goes on increasing. And now look, kinetic energy has reached thousands. So this is what is known as instability. But that is because we are using a very inefficient, as I said, we are using this Euler method for integration. In the next class, I'll tell you about a way of getting out of this type of instability. So the main thing I wanted to illustrate with this example was that the soft particle method can be unstable if your time step is not correct. A simple way of correcting it is to just have some sort of predictor corrector method which will reduce the time step to ensure that the instability doesn't occur. And that's what is there in this program called Run PC. So there I'm running another code called box PC. The first one was just box. This is box PC, which has this predictor corrector thing in there. So if I do run PC, then I think we'll get slightly better results. Okay, so this is the initial. It runs for a while. Okay, this doesn't look so bad. The velocities look quite reasonable. Again, here this is for kV equal to 0. That means the coefficient of restitution is 1, kinetic energy is constant. So in this case, because we have taken the correct time step, the system is not unstable, and it. So again, for the next round also, same thing, kinetic energy remains constant. And for the third time we run it, again notice all the arrows are quite reasonable size, and also you see beautifully the kinetic energy remains constant. So this is one check that you must have. This is the final thing, and which compares where you have a constant step, you see how the kinetic energy just blew up, and this is when you have a variable step, the kinetic energy remains constant. So I'll tell you about this predictor corrector method and so forth in the next class. And I think the final thing is run PC2. This is the same thing but with running it with a coefficient of restitution that is 0.9. This is the initial condition. After some time, and you see kinetic energy is coming down because coefficient of restitution is 0.9. Velocities are reducing. Run it 3 times, velocities, kinetic energy has come down even more. And again, as in the previous case, if we plot kinetic energy raised to power minus half versus time, you get a nice straight line. That you can prove theoretically also. Okay. So with that, I'll stop. Again, when you are ready to try out these programs, I'll upload these today. I'd like you to try them out. Then on Thursday, if you have any questions, then in the class, part of the class could be a tutorial on how to actually run these programs and play around with them. Okay. Okay. So that's it. Thank you, and see you now on Thursday.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir. Bye. Bye.
Bye, sir.